Hey guys, this is Professor Janacek, and I want to talk about points of inflection. To begin with, we'll let f be a function that's defined at an x value c. Now, we'll let f be differentiable on an open interval. If f prime is increasing on the interval, then f is concave up on the interval. And if f prime is decreasing on the interval, then f is concave down on the interval. And finally, if f is continuous at c, but f changes concavity at c, then we say that f has an inflection point, or a point of inflection at c. So, looking at possible points of inflection, we can find these by simply letting f double prime of x be equal to 0, and we'll let f double prime of x be undefined. We'll call these points x equal to d. So d is the value of x, where f double prime is 0 or f double prime is undefined. Now, we have something called the second derivative test. We'll let L be a number to the left of d on the number line, and we'll let r be a number to the right of d on the number line with only one value of d between them. So we don't want two d's between one L and one r. Now, here's the fun part. According to the second derivative test, if f double prime of L and f double prime of r have unlike signs, then there is an inflection point at df of d. Otherwise, there is no inflection point at the point df of d. So let's talk briefly what we're saying here. If you recall that increasing and decreasing can be determined by finding the derivative. Well, I want to know if f prime is increasing or decreasing. So that means I want to take the derivative of f prime, which means we're now looking at f double prime, and that's why it's called the second derivative test. So, moral of the story, the exciting part is, if f double prime of x is less than 0, then f is concave down. And if f double prime of x is greater than 0, make sure you understand, less than 0 is concave down. Greater than 0, then f is concave up. So again, we're looking at the second derivative. Don't forget about the first derivative. The first derivative told us increasing versus decreasing. But here we're looking at the second derivative, which tells us concave up versus concave down. So let's try an example. Let's take f of x is equal to e raised to the negative x squared. Very exciting little function there. We will need both the first and second derivative, so let's take a look at that. F prime of x is, well, the derivative of e is simply e, repeat that, but then the chain rule says we have to multiply by the derivative of that exponent. Fun. So we have e to the negative x squared times the derivative of negative x squared. Well, that's negative 2x. So this simplifies to negative 2x e to the negative x squared. But we're looking at the second derivative test, so that means we're going to need to take a look at f double prime as well. Ooh, so now we need to take the derivative of this. Notice that we have, well, we can write it this way, negative 2x times e to the negative x squared. So I've got two things that both have x's and they're being multiplied together. Oh yeah, there it is, multiplication, which means we will need the product rule. Now there are several versions of the product rule because you can commute both multiplication and addition. Let's go ahead and write it this way. I'm going to start with the derivative of the first part times the second part plus the first part times the derivative of the second part. All right, so what does that give us? The derivative of negative 2x is simply negative 2. And keep that second part e to the negative x squared as is, plus the next part we have just negative 2x times the derivative of e to the negative 2x. Now notice what this is here. That is my original function. So when I want to take the derivative of that, well, that's just f prime. Ha! How nice is that? Moral of the story, this derivative of e to the negative x squared is simply negative 2x e to the negative x squared. Lovely. All right, simplify this just a bit. We get negative 2e to the negative x squared minus 4x squared e to the negative x squared. I think it will be nice to go ahead and factor out, let's see, we can factor out both a negative 2 and an e to the negative x squared. Oh wait, you know what, that's going to be a positive. You know what, let's not factor out the negative. Let's leave that in. You could if you wanted. It's really up to you. So if I just factor out a 2e to the negative x squared, that gives us, well, it would be negative 1 plus 2x squared, but I'm going to turn that around and write it as 2x squared minus 1. Watch, make sure you understand that. I did commute those. Yes, I did. I turned those around. Make sure you understand that. All right. Well, now for our possibilities. In order to find those possible inflection points, we will set this thing here, the second derivative equal to 0, and we'll also have to take a look at the situation where this is undefined. Okay, well, let's start with the 0 one first. Remember, e is a positive number. It is never equal to 0. So this tells me that 2x, that's supposed to be an x squared, guys. 2x squared minus 1 would have to be equal to 0. 2x squared minus 1 equal to 0. Let's see, solve that. Move things around a bit. We would get that x is square root, positive or negative, square root of 1 over 2. Square root of 1/2. Rationalize that denominator and you should end up with a positive or negative square root of 2 over 2. And the only time this would be undefined, well, remember, that's a polynomial. That's never undefined. This would only be undefined if its denominator is undefined. So let's just go through that. So that would mean 2 times 2x squared minus 1 over e to the x squared is undefined. but this would only be undefined if its denominator is equal to 0, but this never occurs. So the only points of inflection we have are x equal to negative square root of 2 over 2 and x equal to positive square root of 2 over 2. All right, so now let's dive into our second derivative test. Okay, so we'll start with x equal to negative square root of 2 over 2. We need to pick something to the left and something to the right, our L and our R. And I'll call this L1 and R1. We'll let L1 equal to, let's see, something smaller than negative square root of 2 over 2. I think negative 1 would work really well. I don't need that in parentheses. Right. Left of negative square root of 2 over 2. Remember, I'm thinking to the left, I went smaller on the number line. We're going in the negative direction. Okay, and to the right, I need something bigger than negative square root of 2 over 2. Well, a really nice thing that's bigger than any negative is 0. And there's no problem with that. Notice my other possible inflection point is bigger than 0. All right. So here we have our point to the left and point to the right. Let's see. Since the second derivative of L1, negative 1, is, let's see, now I'm looking at the second derivative. Remember what we're looking at. We're going to evaluate this bit right here. I guess I can remind myself of this. So this is f double prime of x, right? Just as a reminder. That's where I'm going to evaluate. That's what I'm going to evaluate with negative 1. So that gives us 2e to the negative of a negative 1 squared. That's going to be just negative 1 times 2x. By the way, that's an x squared. 2x squared minus 1. I don't know that that was any better. 2x squared minus 1. There we go. Evaluate that at negative 1. That gives us just a 1, which is 2 over e, right? E to the negative 1 means e is in the denominator. And by the way, notice this is a positive number. All right. And f double prime of 0. Okay, again, looking over here, evaluating this for x equal to 0. What does that give us? Well, that's 2e to the 0 times negative 1, which gives us a negative 2, which is less than 0. All right. Notice what's happening here. To the left, of x equal to negative square root of 2 over 2 is concave. It's negative. I'm sorry, it's positive, so it's concave up. And right is negative, so that is concave down. So let's see again. Concave up to the left, concave down to the right must mean there's a point of inflection there in between. All right, let's take a look now at the other point, at x equal to positive square root of 2 over 2. The numbers to the left and right of this I'll call L2 and R2. So let L2 be something smaller than square root of 2 over 2. Oh, I think 0 would work. And something to the right, something larger. Well, again, I think positive 1, and make sure you understand that. Make sure you see that positive 1 is to the right of square root of 2 over 2 on the number line. All right, since the second derivative of 0, now actually we did this one already. Again, I'm really just evaluating this for x equal to 0, which gives us 2e to the 0 times negative 1, which is negative 2. Of course, we saw that over here with r1, actually, but that is negative. And the second derivative at 1, again, we're evaluating f double prime for x equal to positive 1. We get 2e to the negative 1 times 1, which is 2 over e, which is a positive number. All right, that tells us left of x equal to negative square root of 2 over, positive, oops, this is positive, x equal to positive square root of 2 over 2. To the left of that is negative, so that is concave down, and to the right is positive, so that is concave up. Again, the main idea is that to the left and to the right, the second derivative has unlike signs there. That means there must be an inflection point. So on this one, to the left is negative, so it's concave down, and to the right is positive, concave up. There's got to be an inflection point in between. All right, so I think we're there. Hence, f has inflection points at x equal to positive or negative square root of 2 over 2. Now make sure you also know how to find the y values, because it'd be nice to have the ordered pair for these points. So make sure you can do that. I don't think it's actually too bad. In both cases, I believe you end up with just an e raised to a power. It's not so bad. But there you go. Enjoy.